Hello, welcome. In this short video, let us look at the proof for the theorem that a dot product of two cosine vectors is equal to a weighted delta function. That is, the sum n equal to 0 to n minus 1 cosine of 2 pi kn over n multiplied by cosine of 2 pi ln over n is equal to n by 2 delta k comma l, where the values of k lie between 1 and L lie between 1 and n by 2. And of course delta kl is equal to 1 when k is equal to L and 0 when k is not equal to L. That's the definition of a direct delta function. So now we want to prove this theorem. So let us start with the left hand side. LHS, the sum n equal to 0 to n minus 1 cosine of 2 pi's k n over n cosine of 2 pi's L n over n. And now by using the trigonometric identity cos of A multiplied by cos of B is equal to 1 by 2 multiplied by cos of A plus B plus cosine of A minus B. So by using this trigonometric identity we have, that is, the summation becomes the sum n equal to 0 to n minus 1 1 by 2 multiplied by cosine of 2 pi k plus L multiplied by n over n plus cosine of 2 pi multiplied by k minus L or multiplied by n by n. Now using the following, that is, the cosine of alpha times n is equal to real part of the exponential function of j times alpha n. So by using this definition we have the sum n equal to 0 to n minus 1 1 by 2 multiplied by real part of exponential of j times 2 pi k plus L multiplied by n. And the second part is plus real part of exponential of j times 2 pi k minus L multiplied by n over n. Now using the standard formula on a geometric series, that is the sum of a geometric series, n equal to 0 to n minus 1 exponential of j 2 pi x into n by n is clearly equal to n when x equal to 0 and 0 when x is not equal to 0, as long as x is less than n minus 1. So now by using this identity, summation of a geometric series of exponentials from n equal to 0 to n minus 1 is clearly equal to n when x is equal to 0 and 0 when x is not equal to 0, as long as x is less than n minus 1. So by using this identity we can clearly see that the first sum, that is summation of real part of exponential of j times 2 pi k plus L multiplied by n is always going to be 0, since k plus L is always greater than 0. That means it falls in this region. Therefore this sum should always be equal to 0. That is sum n equal to 0 to n minus 1 exponential of j times 2 pi k plus L multiplied by n over n is always equal to 0, as k plus L is always greater than 0 under the given initial conditions. And similarly for the second sum we have n equal to 0 to n minus 1 exponential of j times 2 pi k minus L multiplied by n over n is equal to n for k is equal to L and 0 for k not equal to L. So by inserting this result, you can clearly see that the initial sum, that is this sum, becomes 1 by 2 multiplied by 0 for the first sum and n for the n times delta of k minus L for the second sum. That is, it is equal to n for all values of k equal to L. Therefore, the sum n equal to 0 to n minus 1 cosine of 2 pi k n over n multiplied by cosine of 2 pi L n over n is always equal to n by 2 delta k L, where delta k L is equal to delta of k minus L. That is, it is equal to 1 when k is equal to L and equal to 0 when k is not equal to L. And this is only true when k and L are between 1 and n by 2. Thus, a dot product of two cosine vectors when their frequencies k and L are between 1 and n by 2 is a weighted delta function. Along the same lines, we can also prove that the following sum n equal to 0 to n minus 1 sine of 2 pi times k into n over n multiplied by sine of 2 pi into L n over n is also equal to n by 2 delta kl. That is, a dot product of two sinusoidal vectors is also equal to n by 2 multiplied by the delta function. And finally, we can also prove that using the same logic that the sum n equal to 0 to n minus 1 cosine of 2 pi kn over n multiplied by sine of 2 pi ln over n is always equal to 0. And note that this cosine and sine are basically interchangeable. That is, the dot product between a cosine vector and a sine vector is always 0 as long as k and l are less than n by 2. Now let us look at the numerical simulations supporting these results. So for the case where we have two cosines, let us look at the Python code. So this is the Python code for displaying the results corresponding to these dot products of cosines. So for the case where we have two cosines, this is the script. This section basically imports the required libraries, and these are the predefined parameters, and then these are the functions for defining the vector and its cosine, and then we plot the results. So if you run this code, you can clearly see that when the frequencies are equal, that is when k is equal to L, we can clearly see that it is k equal to 4 and L equal to 4. We can see that the sinusoids are exactly same, and the sum is clearly equal to n by 2, where n is 100 in this case. So we display the result, it is equal to n by 2. We calculate the value dot product of the two vectors here, z equal to sum of y1 and y2, where y1 and y2 are the cosines. Now when we change them to sinusoids, now when the frequencies are different, that is when k is not equal to L, say for example 3, see that the value is practically equal to 0, that is minus 4.1 into 10 power minus 15, which is practically 0. That is when the frequencies are not equal, the dot product is clearly equal to 0. Now let us look at the simulations when both of them are sinusoids rather than cosines. That is when the frequencies are not equal, we should get a 0, which is so we have minus 4.49 into 10 power minus 15, which is practically 0. Now when the frequencies are exactly same, we should get n by 2, which is equal to 15. So n equal to 100. So if for the sinusoids, that is for this result, when the frequencies are equal, we have n by 2, and when frequencies are not equal, that is when k is not equal to L, this is equal to 0, since it is a delta. Now when one of them is a cosine, other one is a sine, we should get 0 for all values of k and L. That is, it doesn't matter whether k is equal to L or not equal. When the frequencies are equal, we should get a 0. So 3.4 into 10 power minus 15, which is practically 0. Even when the frequencies are not equal, that is when we have different frequencies, even then the result is clearly 0. Thus we can clearly see that the cosines and the sines are basically orthogonal functions, and that is the reason why they are used as basis functions. Thanks for watching.